Welcome to lecture number 3 for ECE 761 Robotic Translation Matrices. Now, a translation matrix is the way to go from one reference frame to another where the origins no longer overlap. That's important for robotics because I want to go from my shoulder joint to my elbow to my wrist. Each of these has a translation. I need to be able to count for the changing reference frame, change the location of the reference frame somehow. That'll be the translation matrix. Since each point is defined by a 4x1 vector, the translation matrix will be this T, a 4x4 matrix, to go from B to A. Now, transformation matrix consists of a 4x4 matrix. This upper left corner is the rotation matrix. This column right here is the translation. That's the translation in the x direction, y direction, and z direction. And W is the scaling factor. To illustrate how XYZ actually is the translation, let's take the point 1, 2, 3, scaling factor 1, multiply by this matrix, where XYZ. If you do that, the new point relative to A is x plus 1, y plus 2, z plus 3. So I'm taking this point, moving it out, 1 in the x direction, 2y, 3z, and here's the new reference frame. I can also zoom with a scaling factor 2. If I put a 2 right here, I get the same point, 1, 2, 3, zoomed in by 2. To illustrate how that works, let's take the arrow that we drew before and my display 3D routine in MATLAB. If I take an arrow and try to display it, or just to illustrate it, here's my arrow up here. I'm going to set it to orthographic projection, that's this section of code. And then I'm just going to change element number 44, that's the scaling factor, going from 0 to 2. If I run that, this is it gets to 2, here it gets bigger, and 0 is zooming away, going up to 2 again. That's the scaling factor, that element 44 in your matrix. If I want to move in the x direction, or y direction, or z direction, I just change these elements. And again, I can see that in MATLAB as follows. I'm going to have dx, that's my displacement in the x direction, go from -1 to +1 as a sine wave. If I then add that to element 1, 4, that's a displacement in the x direction. Notice that the arrow, the shape stays the same, there is no rotation, just the displacement moves back and forth in the x direction. If I want to move in the y direction, change element 2, 4, and that takes the arrow and moves it in the plus y direction. There's the minus y direction. Back to 0. Element 3, 4 is the z coordinate. That moves you in the plus z direction for +1, minus z direction, and back up. Now, there is no reason you can't have a rotation and a translation as well. Just keep on changing the displacement and rotation. I can spin the arrow and move it. That's important because, again, for a robot, I want to go from shoulder joint to elbow joint. That's a translation plus rotation. Then go from elbow to wrist, another translation and rotation. So good note, I can do translate, rotate. With the two together, I got a rotation plus a translation. And here's an example of that. Mixing translation and rotation, I am translating the x-axis and rotating by the z-axis. So again, the two work just fine together. That leads to the third homework set. Homework set number 3 is to convince yourself that translation matrices really do work. Take the shape that you had from homework set number 2 and move it about the x-axis, y-axis, and z-axis, just to convince yourself that, yeah, sure enough, the XYZ elements determine where the next reference frame is. And the write-up is similar to homework set number 2. You can make a YouTube video, you can share your screen with me on Zoom, or you can just take some screenshots, whatever is easiest.